Welcome to The Explainer. Today, we are breaking down the absolute science that makes modern flight possible. And we're going to do it by looking at its most crucial and, completely invisible component, the atmosphere.
I mean, seriously, think about it. This was the massive challenge for the pioneers of aviation. They somehow had to turn the invisible, totally unpredictable air into a stable, predictable roadway for their newfangled flying machines.
Exactly. Early pilots, they had to be detectives of the sky. They had to learn how to read the air, constantly searching for any clues that would give them two absolutely vital pieces of information: how high they were and how fast they were going. So, to solve this huge puzzle, they first had to really, truly understand the air itself. All right, let's dive in.
Okay, so the air all around us, it's basically a cocktail of gases. Yeah, it's mostly nitrogen and oxygen, but the key thing is this mixture has weight. It has substance, even if we can't see it. And that substance is exactly what airplanes push against to get off the ground. Now check this out. This number, that is the weight of the air in a typical classroom. We're talking about the same weight as 4 adults. So you see, air isn't just nothingness. It's tangible. It's heavy. And that weight is what makes flight possible in the first place. And this heaviness of the air, well, we call it density. And it changes. As an aircraft climbs higher and higher, the air gets thinner. It becomes less dense. And that's a big deal because it means there's less stuff for the wings to push against to create lift and less air for the engines to breathe. It directly impacts the plane's performance.
Air pressure. Now that's caused by the sheer weight of all the air in the atmosphere stacking up and pressing down on everything below it. The best way to think about it is like you're at the bottom of a giant invisible ocean. The deeper you are, so the closer you are to sea level, the more all that weight is pressing down on you.
But here's the thing. This ocean of air, it isn't uniform at all. Nope. It's actually made up of distinct layers, and each one has its own set of rules that pilots absolutely have to understand.
We live in the very first layer, the troposphere. This is where pretty much all of our weather happens. It's the densest layer, and it's where just about all commercial aircraft fly. They typically cruise around 11,000 meters, trying to get right up near the top of all that turbulent weather.
Now go above the troposphere and you hit the calm, layered stratosphere. The air up here is thin, it's dry, which makes it a really stable region, perfect for high-altitude flight. This layer is also home to the ozone layer, which, is pretty important for protecting us from the sun's UV radiation. And this just brilliantly illustrates how extreme this environment really is. The famous U-2 spy plane operated deep inside the stratosphere, flying at altitudes so high they were practically on the edge of space, way, way above any commercial traffic.
The extreme pressure differences at these altitudes create an incredibly dangerous environment. This tragic incident is just a visceral reminder of the physics at play. At cruising altitude, the pressure inside the cabin is way higher than the thin air outside. If you get a breach in the fuselage, that can lead to a catastrophic explosive decompression.
And as we go even higher, the extremes just get more and more pronounced. In the mesosphere, you'll find the absolute coldest temperatures in our entire atmosphere. But then you go up to the thermosphere, and direct solar radiation makes temperatures just skyrocket to over 1,700 degrees Celsius as the air finally thins out into the vacuum of space. Okay, so with this new understanding of how the atmosphere works, early aviators finally found their crucial clue. They had an aha moment. They realized that air pressure changes in a predictable way. The higher you go, the lower the pressure gets. And that realization led to the invention of this brilliant little device, the altimeter. Just think of it as a really, really sensitive barometer. Inside, there's this sealed metal capsule that expands and contracts with tiny changes in air pressure. And then, a clever system of gears magnifies that little movement, turning it into a readable altitude right there on the dial. So smart.
But of course, there was one final problem. An altimeter measuring local pressure is great for one plane, sure, but what about hundreds of planes in the sky at once? The real atmosphere is constantly changing with weather and location. To fly safely, everybody needed to be using the exact same reference point.
So this is the crucial point right here. Aviators realized they needed to invent a theoretical, kind of an idealized model of the atmosphere, a universal baseline so that every single altimeter on every single aircraft would be calibrated to the same standard. They all had to be speaking the same language.
And this is what they created, the International Standard Atmosphere, or ISA.
And let's be clear, it's not the real atmosphere. It's a perfect mathematical model that acts as a universal map of the sky for all of aviation.
The ISA starts with a fixed baseline, these exact conditions right here at sea level. From that single starting point, it uses a fixed lapse rate. That's the predictable rate that temperature drops with altitude, to calculate the standard pressure for any given height. This ensures every pilot is using the exact same map.
And believe me, this was not a small effort. We're talking decades of work, with international organizations all coming together to refine and extend this standard map of the sky. It's now the absolute bedrock of modern aviation, essential for everything from air traffic control and flight planning, all the way to aircraft design itself.
So the International Standard Atmosphere, it was a brilliant solution for its time, but it leaves us with a pretty big question for the future, right? As our climate changes, will this idealized map still be accurate enough to keep us safe in the skies? Thanks for watching.